Well, hi. We're going to have a very interesting look today at an application of differentiation, specifically the area of kinematics, a much misunderstood area in a specific part to do with speeds and average speeds. So that's the part I want to really emphasise, as well as covering the main points of a typical applications of differentiation question in the area of kinematics. So let's get going and have a look, okay? Right, we've got a particle starting from the origin, has a velocity of v equals 2t minus 4. And t, of course, being time, in this instance, is greater than or equal to 0, where t is measured in seconds, and x is the displacement from the origin measured in centimetres. Find A, the initial velocity, B, the acceleration, and show that it is a constant, C, the position at t equals 2 seconds, D, the average velocity over the first 3 seconds. No problem so far, but E, watch like a hawk, guys, because there's a booby trap in there. It's average speed over the first 3 seconds. Now I'll explain that as we go on, okay? Ready? Pencil sharpened, heads into gear, nice cup of tea. Off we go. Well, part A today, hooray, the initial velocity now. Okay, come on. You think about that. How are you going to do that? Yes, of course, you're going to set t equal to 0, and you're going to get, yes, 2 times 0 minus 4, which is minus 4 centimetres per second. Now, if you were thinking of a number line, an x or t number line, a horizontal number line, you would consider that that is 4 centimetres per second, and the minus means it's going to the left, okay? Velocity is a vector. It has a magnitude and a direction. And in one directional motion, or one dimensional motion, rectilinear motion, we are considering plus as moving to the right and minus as moving to the left, okay, in the negative direction. Got it? Thank you, Mr. Box. All right, part B, for you and me, the acceleration. Well, do you remember that the derivative of the velocity is acceleration? So we've just got to do the derivative of that expression, and we get 2 centimetres per second every second, or centimetres per second squared, or centimetres per second, which means, firstly, that is a constant. It's just 2, and it means that every second the velocity is going up by 2 centimetres per second, all right? So the acceleration is towards the right, it's positive, okay? So our little particle, if you imagine that, if it's zooming along at minus 4 centimetres per second, every second it's going to change by plus 2 centimetres per second, if you get that, right? Yes, so after the first second it'll be doing minus 2, after the second it'll be doing 0, after the third second it'll be doing plus 2, and so on, right? There you go. Thank you, Mr. Box. Now, part C. Isn't this fun? The position that means the displacement, guys. The position means the displacement. Position means relative to the origin, and all of our positions are relative to the origin here, so they're displacements, yes? All right, so at t is 2 seconds. Well, I think this calls for some anti-differentiation, all right? Because to get from the velocity to the displacement, you have to anti-differentiate, don't you? And then, of course, you've got the c term in there, the constant of integration. We have to sub in, starting from the origin. So that's in the clue in the question up here, starting from the origin. So we know that when t is 0, x was 0. So if you plug that in, I think c is going to come out to be a great big 0. Here we go. Excellent. So therefore, we know that c is 0, and we know that x is t squared minus 4t. Okay, okie dokie. And we're going to put a box around that, I think. Oh, no, we're not. Oh, sorry. Sub t equals 2. What are we trying to do again? Oh, yes, the position when t is 2 seconds. Right. Okay, put it in. And we get this. A minus 4 centimetres. Now, that's very significant. The reason I asked you for that will become clear in a moment. Now we've got a box. Thank you, Mr. Box. Okay? So at the end of 2 seconds, we're at minus 4 centimetres, ladies and gentlemen. And that is significant. Oh, I think I'll tell you. I can't keep a secret. Because did you hear me say when I was talking about the velocity before, that after 2 seconds, if the acceleration is plus 2 centimetres per second every second, then at the when you're starting, it's minus 4 centimeters per second. After 1 second, minus 2 centimeters per second. After 2 seconds, 0. So that's when it's 0. That's when it stops and changes direction. Okay? I'm going to explain that as I go, but I think you might be getting the message of what I'm talking about here. It changes direction when t is 2 seconds. We'll show a little graph in a minute. What's this? The average velocity over the first 3 seconds. Well, that's easy. The average velocity is just simply the overall change in displacement over the overall change in time. It's not an instantaneous thing at all, okay? So you just look at the end points of the displacement, 3 seconds, 0 seconds, subtract the 0 second displacement from the 3 second displacement, and do the same thing with time. So, what am I saying? That's the displacement at 3 seconds, which is going to be minus 3 centimeters. Now, the displacement at 0 seconds, as we know, was 0 because it started off from the origin. So therefore, that we've got all the information we need on displacement. Therefore, the average velocity will be x at 3 minus x at 0 over 3 minus 0 seconds. T equals 3 minus t equals 0. Yes? Okay, get it? That's how you do average velocity. So it looks like it's minus 3 minus 0 over 3 minus 0, which is minus 3 over plus 3, which is minus 1 centimetre per second average velocity over the first 3 seconds. Yes? Now here comes the crunch up. This one here, this is the one I really want you to watch. The average speed over the first 3 seconds. Alright, now the average speed is just the total distance over the total time. And that's a logical concept that you're used to dealing with, okay? If you went on a trip somewhere, you'd divide the total distance by the total time to get the average speed, wouldn't you? Yes. But the problem with this little beastie is that it changes direction. Look at this graph. Yes. Now you see that? Look, this is really, really important to get this. You see now, v, according to the equation, was up here, was 2t minus 4, wasn't it? So look, here's the graph, 2t minus 4. We're starting off when t is 0 because there's no such thing as a negative time, so there's no left-hand side to this graph. Okay, now, you see what's happening here. Look, when t is 0, it's doing minus 4 centimeters per second, as I said, and it's going up every second by, according to the acceleration, by 2 centimeters per second. So it'll be minus 2 centimeters per second at 1 second, and it'll be 0 at 2 seconds. In other words, this is the point where it stops going backwards, is stationary, instantaneously, momentarily stationary, and from that moment onwards it starts going forwards because the velocity is in the positive. Okay, it's above the t-axis here, it's below the t-axis there where the velocity is negative. So therefore, in real life, you can imagine, if I just got my little hand here and get you a little squiz across the page, this could be the starting thing, stops at 2 seconds and then starts going forward like that and speeding up. Do you get me? Yes, that's what you do. So therefore this beastie has changed direction. Therefore if it changes direction in the middle of the time interval that you're trying to work out, which yes it has done, because we're trying to work out the average speed in the first 3 seconds, right? Therefore the displacement will not be the same as the distance, right? It won't be. Of course it can't be, because the displacement is just simply where you end up compared to where you started. The distance is the total distance, both forwards and backwards, okay? So we've got to work out the total distance. So what we have to do is split up the journey into the backwards bit, take away any plus or minus from displacement just to get a length, then do the same thing for the forwards part of the journey, and then add up those two components of the journey, and then you get your total distance. If you didn't get that, have a look at this and we'll show you. Yes, when t equals 2, v is 0, and the thing changes direction from negative velocity to positive velocity. Yes, that's what the graph shows. Yes, so we need to find the distances for, yes, the first 2 seconds firstly, and then secondly for the second to the third second. Okay, that's the, what am I trying to say? From t is greater than or equal to to, but and up to and including 3 seconds. Yes. And by the way, I just did a little magic trick. I had the inequality around the wrong way, so I've just fixed it up. I've just paused the video and fixed it up so you wouldn't get confused. All right, you right now? Yes, so we're going to work out this distance travelled in this time interval from the start to the end of the second second. Then we're going to go from the end of the second to the end of the third second. Work out that distance and add up the two individual distances. Yes? Good. Let's go. Now, alright, so therefore, when at the start of the journey we know that when t was 0, x was 0. Now, okay, when t was 2, x was minus 4, we'd already discovered all that, I think. Didn't we? Yes, we did. So here's our number line. Now, I'm just showing you, watch this. This is a little animation or something. The distance, yes, there it goes. Oh, did you see that? I moved backwards from 0 to minus 4. The distance is 4 seconds. It's not minus 4, it's just 4 because distance doesn't have any sign. It's not a vector. It's called a scalar, which means just a length, no plus, no minus, no nothing, just a length, okay? Right, that's that bit. Now we've got to see the second part of the journey, right? Okay, working out x, it looks like it's minus 3 centimetres, so therefore that's the position at the end of the third second, right? So here's your number line. Now, okay, yes, see I've shown it moving from minus 4 to minus 3 in that third second, right? So what's that distance? Yes, it's 1 centimetre. Therefore, the total distance travelled will be 4 from 0 to 2 seconds plus 1 from 2 to 3 seconds, which gets us 5 centimetres. Now, we're a breath away from victory, guys. So we're going to say that the average speed is the total distance over the total time, which is 5 over 3 centimetres per second. Thank you, Mr. Box. And that's it. Now, you see the danger of trying to work out average speeds without drawing a little velocity time graph. I really recommend you draw that velocity time graph. And if your trajectory crosses the horizontal axis somewhere within the time interval you're trying to work out the average speed for, you better watch out because you have to break it up into two separate journeys, strip the pluses and the minuses off any displacements, and just add them up as distances, okay? Then divide by the total time. Okie dokie. Thank you so much for listening. I hope you enjoyed that little presentation, and we'll see you next time. Bye.